Hello and welcome to the fifth lecture for 462. This is called Fine versus Coarse. Okay, so this is going to be a video, and what I'm going to do is I'm going to go through the slides with you in this format. Now, let's go back and think about engineering and materials in engineering, and let's think of concrete, because we are all familiar with concrete. Let's say, well, concrete has a strength, of course, that depends on various characteristics of the concrete. For example, the water-cement ratio with which the concrete was poured, the time of curing, the sizes of the aggregates make a difference in the strength, and the additives, right? So that is what controls the strength of soil, and how the soil is, concrete, and how the concrete is going to react or act actually when it is loaded. Okay, what the deformation is going to be before failure, also what the stiffness is going to be for concrete. Those parameters define that for concrete. For soil, what dictates the stiffness and the strength is the way in which particles are assembled together. Okay, and that's called the fabric. The way particles are assembled together. And we already know, we said before, that the fabric of fine-grained particles is controlled by the water content, W. The amount of water in the soil is going to control the fabric, okay, of that soil. And not only that, but also the chemistry of the water, meaning the ions that are present in the water and the molecules, say, that are present in the water. Now, for coarse-grained particles, the fabric is coarse-grained particles or soil. The fabric is controlled by not water content, but it's controlled by essentially two things. Okay, one is the distribution of sizes, which we're going to talk about in this lecture, and distribution of, let's say, sizes, diameters of grains, and also the shape of the grains. Okay, so as you can see, there is, in summary, the behavior of soil is controlled by how the particles are assembled together. For fine-grained soil, what controls how the particles are assembled together is the water content and also the chemistry of the water. Okay, for coarse-grained soils, what controls how particles are assembled together is the distribution of sizes, okay, and the particle shapes. Let's talk about the next slide. Notice that we are going to now talk about coarse-grained particles only. Okay, soils that are coarse-grained, that is sand or gravel. Okay, here we have a definition, and this definition is actually for any kind of soil. The coordination number, that is the number of neighbors per particle. Okay, so if you have a soil mass and you pick one particle of that mass and you count the number of other particles it is touching, then that is the coordination number. Okay, so for this particle, 1, 2, 3, 4, 5. Okay, that is just a definition that we have to keep in mind, because we're going to go back to it and refer to it every so often. Okay, here are two definitions that are very important for coarse-grained soil. The Emax, or the maximum void ratio, possible, and the Emin, which is the minimum void ratio, possible. Okay, now you know that if a soil, coarse-grained soil, exhibits a large void ratio, then it exhibits a minimum density or a low density. Okay, remember that density is rho. If the soil has a low void ratio, right, that means that the volume of voids over the volume of solids is low, then the soil has a high density. Okay, now low and high are definitely quantitative terms, but they are more qualitative, I guess. Emax and Emin correspond to the maximum possible and the minimum possible void ratios for a soil. Okay, So let's say that you go to the beach. So let's say that you go to the beach and you pick up some dry sand and you place it in a bucket and you take it to the lab. Okay? You have this sand in the bucket, and you have the bucket in the lab. You can weigh the sand and determine the mass of solids, okay, because the sand is dry. And then you can compact the sand inside the bucket so that it is the most compact you can get it, okay? It has the highest density possible. If you determine the void ratio of that sand, you will get E min of that sand, okay? Maybe something like 0.5. That's an example, okay? That doesn't mean that E min is 0.5 always. It's just for the sand that you took to the lab. Now let's say that you run another test in which you can actually assemble the grains in the bucket with the loosest possible configuration, that is with the smallest density possible. If you measure the void ratio of that soil in the bucket, it's the same sand, just assembled in a different configuration. It has a different fabric. You will get E max, okay? And you may get something like 0.8. That's an example again for that sand, okay? That means that your sand that you brought from the beach has a minimum void ratio of 0.5 and a maximum void ratio of 0.8. Now, let's say that you go to another beach, maybe in the Caribbean, okay? And you bring back some of that sand in a bucket. You run these two tests, let's say. You determine the E min and the E max. For that sand, you may get an E min of 0.52 and an E max of 0.72, whatever, right? So what I'm trying to show here is that E min and E max for one soil are not the same as what they are for another soil, okay? Each soil, and I'm talking about coarse grain soil, has an E max and an E min, and these are determined in the lab, okay? Now, why do we want to know what is the maximum void ratio a soil can achieve and what is the minimum void ratio that soil can achieve? Because we are going to compare those void ratios, which are the limits or extremes, to the void ratio of the soil in the field, okay, in situ. In situ means in the field. That's just a fancy word for it that we use in geotech. Okay? So, let's go back to the example that where you have the sand from San Diego, let's say, and the maximum void ratio is 0.8 and the minimum is 0.5, okay? And let's say you're going to build some structure right there on the shore, okay, on this soil. Now, what you would like to know is what is the status of the soil in the field relative to the extremes. Okay, so let's say that you go to the field and you measure the void ratio in the field and it is 0.8. Then you go back and say, oh look, the soil in the field is actually at its minimum density possible because its void ratio in the field is 0.8, which is the same as what I measured for Emax. So then what you would say is that that soil is very, very loose. It's the loosest possible. Now, let's say that on the other hand, let's say that you go to the field and you actually measure the void ratio in the field and you get 0.5. In that case, you could say, this is great because my soil in the field has the maximum density it can possibly have. So I don't have to compact it in the field. Okay? It's already compacted by nature. This is because the E in situ, which is 0.5, I determined in the field, is the same as what I measured in the lab to be E min, 0.5. So this equation here, which is called the relative density, allows us to determine or to quantify the comparison between the maximum and minimum void ratios and the in situ void ratio. Okay, here's the definition. It's very simple. E max minus E in situ divided by E max minus E min. So E max and E min, yes, they're calculated in the lab, so they are essentially given. Okay, you can determine them in the lab. Let's say if you work in the field, you could hire a lab company to determine E max and E min for you for your soil, for your site. Okay, and you can hire another company or you can do it yourself to determine the in situ void ratio, the void ratio of that soil in the field. Okay, so if you calculate, if you have these four, well, there's three of them, this one, and this one. If you have the three, then you can determine the relative density, and then you can use this very simple table to label your soil in terms of its density. So very loose or very dense, those are the extremes. So look, let's say your in situ is 0.8. That coincides with Emax, 0.8. 0.8 minus 0.8 is 0. 0 over 0.8 minus 0.5 is 0. 0 is here. So your soil is the loosest possible. Okay? If your in situ is 0.5, then 0.8 minus 0.5 is 0.3, and 0.8 minus 0.5 is 0.3. The ratio is 1. Here's 1. That is 100% relative density. The soil is at its densest possible. Okay, clearly we almost never find soils that have a relative density of 1 or 100%. Okay, that's what this is percents. Okay, or 0. These are extremes. We almost never find the soil in the field at Emin or Emax. Generally, we find it around here. Okay, loose, medium to dense, or sometimes actually very dense. It's very hard to find the soil in the field in a very loose status or with a very loose relative density, but you can find them. In that case, of course, you would want to compact them, or compact the soil so that you get a relative density that is higher, because remember, a soil that has a high density is one where the coordination number is high. So for each particle there are many contacts. So that soil is strong and stiff, because if you load it, the particles need to move, each particle needs to move relative to many others and grind against many others for the soil to deform. Okay? That is the reason why a dense soil is stronger than a loose soil and stiffer, because a loose soil has a low coordination number and a dense soil has a high coordination number. If each particle has many neighbors to grind against, that would be for dense, very dense, right? Then the soil would deform only a little bit, or it would be hard to deform the soil for a given load. So it's all about coordination number and fabric, which are of course related, right? Okay. Okay, so we know that coarse particles, or coarse-grained soils, exhibit configurations that are associated to extremes. Okay, Emax is the extreme where the soil has the minimum density, maximum void ratio, and Emin is the situation or the state of the soil when the void ratio is the smallest possible and the density is the highest. Okay, this is what we would want, right, to encounter or have soil, because we want a soil that is very dense, as dense as possible, hopefully. Okay, this is for coarse-grained soils. We never talk about Emax and Emin for fine-grained soil. Okay. Okay. Now, the next slide is actually this slide right here. This is the next slide, right? And this slide has a grain size distribution, etc. right here. But before we get to that slide, we're going to have some background as to what this means right here. So let's move this location here. Okay, so the idea is as follows. We're going to start with a kind of like a crazy test, okay, or data analysis. What we're going to do is we're going to say, look, there's about 45 people in this course that you're taking, okay? And what we would like to know, what are the heights of these 45 people, the distribution of heights, okay? So what we're going to do is we're going to create a plot, okay? We're going to put here height, feet, okay? And here we're going to put number. Okay? We're going to say number smaller than or equal to. That is, the number of people smaller than or equal to this height. I know that's kind of weird English, but you know what I mean. Okay. So 5, 6, 7. Actually, sorry. That's going to be the next slide. Here we're going to say, or the next plot. Forget about that. We're going to say the number of people. Okay? So how many people in the class are 7 feet tall? 0, probably. Okay, I'm guessing because I don't know, I haven't seen any of you, so I don't know if there's a giant in there. But I am expecting there's that nobody's 7 foot tall. Okay, 7 feet tall. Now, what about 6'6"? 6'6", that's very tall. Maybe 1. Okay? What about 6 foot tall? Maybe, I don't know, 5? Let's go to the other side. What about 5 feet? Maybe 2. 5'6". 5'6" is about the average height in the US for all the population. So I would say there's many. Maybe like, I don't know, 30. Okay? What about 5'4"? 5'10". Okay, so what we get here is called a distribution of heights. Okay? So if we were to say, okay, 6'1", 6'2", 6'3", etc., we'll get probably something like this. Okay? Who's the tallest person? Tallest person is this person right here. Okay? And who's the shortest? This person right here. This is 1. Okay? And 1. What is the average height in the class? Well, it's the peak of the distribution. Okay? And that would be, I don't even know, 5'7". Okay? Now, what does this have to do with soil? You'll see in a second. Let's say now that we want to plot this data in another format, which is the format that we use in soil, and you'll see in a second in geotech. Well, let's put it right here. I hope that you can see. Yes, you can see. I can see it in the screen. Okay. What we're going to do here is we're going to say number of people smaller than or equal to this height, like we had here, but I kind of jumped. All right, 6, 5, 7. Now you know what we're gonna do? We're gonna jump one more step, and we're gonna say not the number of people. We're gonna say the percentage of people in the class that have a height smaller than or equal to this height. This is in feet. Okay. Up here is 100%, down here is 0. So, let's see. What percentage of the class has a height that is smaller than or equal to 7 foot? Well, 100%, because everybody is smaller than 100. Sorry, everybody is smaller than 7 feet, right? What about 6'10"? What is the percentage of the class that has a height smaller than 6'10"? 100%. Everybody is smaller than 6'10". The tallest person is 6'7". That's taller than Michael Jordan, but that's fine. So let's say that's the case. 6'7". 6'7" is around here. That's the tallest person. So what percentage of the class is smaller than or equal to 6'7"? 100%, because there's one person that is 6'7". Okay, that means that the equal sign stands, right? It's less than or equal to. All right. What percentage of the class is shorter than 5? Shorter than or equal to 5 feet? Well, there's one person, right? that is 5 feet, we said, tall, and so we say that that percentage is 1 over 45, right? So it's a very small percentage. That's that point. Okay? What percentage of the class is smaller than or equal to 6 feet? Well, most people are. About 90% of the class is shorter than 6 feet. Shorter than or equal to 6 feet. Okay? Etc. So what we get here is a plot that looks like this. This is 50%, right? This line. Where do you think that line connects to? Not to scale here, but this is 5.7. The mean. Okay? So 50% here corresponds to the mean. This curve has the same information as this curve here, but it's just plotted in a different way. Okay? This is the type of plot or type of data display that we use for geotechnical engineering. Now, clearly in geotechnical engineering we don't count the number of people and the height and what people are these. What we do is, of course, we count, and we actually don't count, we weigh, and we'll talk about that in a second, but we do this for the grains in the soil. Okay, we want to know what is the smallest grain and what is the largest grain, what are their sizes, what is the distribution of sizes in our soil. Okay, we could have a soil that has all the particles of the same size, or almost the same size, let's say, or we could have a soil that has many different sizes of particles. Okay, and what we use to characterize those differences is this plot, which is called the grain size distribution. This is a height distribution. This is a height distribution. What we have is a grain size distribution. Okay, which is this. Okay, this is a grain size distribution, 0 to 100. With size here, not height, but size in what is called the diameter of the grain. Okay, and here's the distribution for a particular soil. Now let's look at the y-axis. It says here percentage finer than by mass. Okay, so this is like saying percentage smaller than or equal to by mass. This should be finer than or equal to. Okay, but typically we don't say or equal to. We don't write that down typically in geotech, but that's what we imply. So this is what it means. Just what we had before, but you have this text here now. This distinction by mass. Okay, by mass. So what does that mean? Well, remember that for our example, for people in the class, what did we do? We counted number, remember? So we said how many people are taller than whatever, or shorter than, sorry. Here, how many people are shorter than? How many people are 6 foot tall? How many people? How many? Right? For soil, we cannot say how many, because we're not going to start counting thousands and millions and trillions of grains, right? So we have to weigh the soil. So this distribution that you see here is not by number, as this one is. This is by number. Sorry. By number, right? This one is by mass, because we weigh the soil. And I'll show you just in a second. I'll tell you some indications as to how we determine these masses, okay, and how we eventually get to this. Of course, it's in the book, and I expect you to read the book, as I said in the welcome video. Now, let's look at the curve. Here's the curve, right? That's for a given soil. Notice that the x-axis is in a log scale, okay? In a log scale. You have to learn, if you don't know already, how to read a log scale. So I'll leave that up to you, because that's beyond the scope of this class. What you have to realize is that the difference between the main tick marks is tenfold, okay? So between 1 and 10, that's 1 times 10, 10. 10 times 10 times 10, 100. 100 times 100 times 10, sorry, 1000, etc. Right? And there is a log scale between each two tick marks, always. Okay, so make sure that you go to Google, to Wikipedia or something and learn how to read a log scale. Okay. Now, what is the largest particle in the soil that exhibits this grain size distribution? Well, that one, 100, smaller than or equal to, right? So then you go down here, boom, and this would be about 70 millimeters or so. I should use my red ID or a ruler to make sure that I know how to read, or that I read the correct number. So I'm just estimating here is about 70 millimeters. That's a gravel, right? Okay. So this soil has gravel. Now, what is the smallest grain size? This one. Okay, 0.001 millimeters. That's clay, right? Because we know that any particle smaller than 0.075 millimeters is fine. And we know that the distinction between between clay and silt is about 0.002 millimeters. Okay, so that's a clay particle. There's a clay particle in our soil, at least one, and there is at least one gravel particle, huge gravel particle, 70 millimeters. Okay, that is 7 centimeters in size in our soil. Okay, so 7 centimeters is it's like from here to here, about that big. So that's not huge actually, like I said, but it's a large size for a soil. Okay, so what we have here is a soil that has clay, silt, sand and gravel. It's a mixture of all soils. Alright, now you're gonna learn later on how we actually use this data to determine, to characterize the soil, that is to formally classify the soil, meaning give it a specific engineering name. Okay, but that comes later. What we need to know is how to characterize this curve that we get based on the parameters, or based on parameters that we can get for it. Okay, so first thing we're going to say here, we're going to note, is that we can take any point along this curve, not just the blue points, but any point along this curve, and give it a special name. Okay? We have selected arbitrarily, actually not really, because we're going to use it in here. Okay, but just let's go back to saying that it's arbitrary. We just say, look, we want to know what is the D60 of the soil. Okay? You could say D60, or you could say D37, or you could say D52, or whatever you want. But here we say D60 as an example. D60 is the 60th percentile diameter. Okay, so D60 is a size. As you can see here, it has units of millimeters. Okay? So what do we say here? We say, okay, look, you want D60? Fine. We go to the 60th percent. We draw a horizontal line, hit the grain size distribution, drop down vertically, and read the size that is associated to the crossing there. That is 1.2.3.4, about 0.44 millimeters. Okay, so that's D60. What is D10? It's shown here. D10, it's about 0.075 millimeters. Okay. What about D50? D50, remember that's the mean size, the average. We disclose that here. Remember this? 50%? That's the mean. 5.7, 5.7 as the mean. So that's a very important size. That's called the mean particle size. And in this case, it is about 0.4 millimeters. Oops. Please use a ruler. Okay? Etc. So you can get the whatever you want, the 100, the 90, the 80, the 72, whatever you want, and determine that size. Okay? Now that you know how to determine these D's, then you can determine these two parameters. The C sub u, which is the coefficient of uniformity, and the C sub c, which is the coefficient of curvature. The C sub u is a parameter that is defined by what is d60 over d10. So in this case, what is it? It's 0.44 divided by 0.075. Okay, that's just a number. That is the answer to Cu. That is Cu. Okay? And what this tells you is that you can, well, what Cu is used for is to determine if the soil is well graded or poorly graded. Okay, what does that mean? Well, that's a name, that's a definition or an adjective that we use to define the soil. So for example, if you ask somebody in the field, hey, what type of sand do you have there? They may say something like, I have a well-graded sand. And you already know that the grain size distribution is such that the D60 over D10 is high. Okay? So it's just a name or a set of words used to characterize the grain size distribution. Now, what does it mean? Well, this is this value divided by that one, right? In this case. So what it tells you is what is the slope of the inside or the inner portion of the grain size distribution. So if the Cu is close to 1, then you have a very steep grain size distribution, in which case your soil is so-called poorly graded, meaning that there is only a narrow range of sizes in the soil. If you have a high Cu, right, then this value is very different than this value, so the slope is less pronounced, let's say, and if that slope is less pronounced, you have a wider range of sizes that is well graded. Okay, there's many sizes in that soil. Now, as you will learn later on, a well-graded soil is able to achieve a lower E-min because small particles can fill the voids comprised or that the bigger particles make, etc. Right? So a well-graded soil can achieve a lower E-min and therefore a higher density. So when you compact a well-graded soil, it is stronger than when you compact a poorly graded soil, which only has a narrow range of sizes. So we would like, if we have coarse particles, this is for coarse, okay, in general, what we would like to encounter is a well-graded soil, well-graded sand, for example, that is compacted, let's say, at a relative density of 95%. If we find that in the field, we're happy because we know that that soil is going to be very strong and stiff. Okay. Now the coefficient of curvature is this one down here. And what you have here is Cc, that's the coefficient of curvature, d30 squared over d10 times d60. Okay, so you essentially have to come here and find d30, for this case is about 0.2 millimeters, square it, divided by this multiplication here, and you get a value for C sub c. This C sub c, the coefficient of curvature, is going to be used later on when we actually classify the soil. Okay, we give the soil a standard name, and that is the topic of the next lecture. Okay, now if we go back to the grain size distribution itself, a very important question to ask is what is the percentage of fines in the soil? Okay, it is important to know, if we have a soil, what is the percentage of fine-grained particles in that soil. Okay, so if in this case and in every case, what we do is we go to the fines threshold, fines versus coarse threshold, right? And we essentially draw a vertical line, and wherever it touches the grain size distribution curve, we draw a horizontal line and then determine what is that percentage. So that percentage, for this case, the percentage of fines for this grain size distribution, for this soil, is 10%. So the soil is composed of 10% fines by mass. Okay? Now, before we move to the next slide, I would like to go very quickly through how we get this curve. Now, ideally, what you will do is read in the book the particular steps required to determine this curve, and you will also learn how to actually create this curve for a given soil in the lab class, 463 class. Okay, but let's talk briefly about it. Okay? This is the way we do it. Remember that the grain size distribution is a distribution that is by mass. That is, we weigh the soil and then we determine what masses of soil in our soil are composed of grains with different sizes. Okay? Now, percent, right, and size, and this is in a log scale. Make sure that, again, remember, you need to know how to read a log scale. Okay? All right. Now, what we use are called sieves. Okay? A sieve is essentially it's like a pan or a cup. Okay? It's cylindrical. Okay? This is a side view. If you look at it from the top, it looks like this. But instead of being a standard pan or a standard cup, let's say, it's a cylinder that has the bottom, that its bottom is composed of a mesh. Okay? Like a wire mesh. Okay? So what we do is we take a bunch of sieves and we stack them. We stack them. We place one above the other. Of course, they are made for this purpose. I'm going to draw this last one like this because it's a different one. Okay? Now, if you look at this, if you stack them like this and you look at this sieve may have, if you look at it from the top, holes this big. Okay? If you look at this one, it's going to have finer or smaller holes. Okay? This one, very fine mesh. Okay? So as you can imagine, what we do is we take this stack, we put the soil in here, dry soil, okay, the soil that is taken to the lab for us to analyze and to categorize and classify. We place it in here, and then we shake with a shaker. We actually have a shaking machine that shakes the sieves, okay, as a group, and so the particles are separated given their size. Okay? This is a pan. That is, the bottom is just a flat sheet of metal. Particles cannot go through this. Okay? Now, this sieve, well, before we go to this sieve, what we do then after we have shaken this, we take each sieve and we weigh it. We take this one and we weigh it. We take this one and we weigh it. We take this one and we weigh it. Of course, each of these may have or may not have particles. Okay? So by doing that, we can separate the particle sizes and we know what is the mass of each range of sizes, and then we plot it. Okay, I'm going to leave it at that. I'll allow you to take the lab and actually learn the lab class 463 and actually learn how exactly we do this. For 462, which is this class, what I want you to know how to do is I would like you to know how to get these parameters. Okay, I would like you to know, of course, what this curve means, etc., how to get the percentage of fines, and later on you'll actually use the curve to classify the soil. Okay, this last sieve is called the number 200 because it has 200 openings per square inch. The size of a hole here, guess what it is? 0.075 millimeters. So any particle that passes this sieve and lands in the pan is a fine-grained particle. Okay, so that's the most important sieve, let's say, because particles that are retained on it are coarse, and particles that pass through it are fine. Okay. All right. That is the way that we determine or calculate the masses of soil that we then use to plot our grain size distribution curve, whatever it may look like. Okay. All right.